Dear students, welcome again. Today's topic number is the EMWG-S2 Electromagnetic Waveguide section 2. The title of the topic is Attenuation in Waveguide. We will be discussing obviously the parallel conducting planes waveguide, which we have now completed its all the field configuration TE and TM modes. Now we will see what the attenuation plays the role inside the waveguide of that parallel plane conducting planes. So what is it? Attenuation. First, attenuation is the reduction in level of transmitted function, any function like E or H fields, as a function of some parameter, usually distance. It is applied mainly to acoustics or the electromagnetic waves and is expressed as the ratio of the power densities. The attenuation of a beam of radiation, that is the reduction in the intensity of the flux density, results from the absorption and or scattering of the waves or particles as they pass through the matter. So attenuation means the reduction in the level of the transmitted wave. We will be taking into account what are the various factors. So the attenuation or the propagation wave constants, now we denote it as a gamma. Let's write it with a gamma m. M are the modes, various modes, values, m having values. So we represent here, we introduce this small m in the subscript. So gamma m is given as the gamma m is equal to square root of the m pi over a whole square minus omega square epsilon mu. Now the gamma m also is equal to alpha m plus j beta m, depends upon the values under the radical, this the square root, and can be wholly real or imaginary depending upon the relative magnitudes of m pi over a and omega square epsilon mu. Means if m pi over a whole square is greater than this value, it will be wholly real, because this will be greater value, this is smaller value in the square root will be some real value. But if this value is greater than this one, omega square epsilon mu is greater than this one, obviously the whole value will be imaginary, because the minus negative, it will give you the negative value, and under the square root negative value is an imaginary value. Thus the two conditions arouse with the alpha m equal to 0 or beta m equal to 0. So it is possible to have propagation with zero attenuation, that is alpha is equal to 0, or high attenuation with beta is equal to 0. It is also seen that the frequency of a wave is also another major criteria determining whether the wave propagation is taking place or not. So let me correct that one thing. Okay, this was repeated. Okay, let me that has been corrected. Whether the wave propagation is taking place or not. So the critical frequency at which the wave starts traveling along the waveguide, or that attenuation condition changes to that of propagation, can be determined from the equation 1. Let us find the condition for the critical frequency. We denote it as Fc, the critical frequency when the gamma m is equal to 0. So this is a particular frequency at which the attenuation is equal to 0. So when we have the gamma m, we put it equal to 0 in equation number 1, what we have m pi over A whole square minus omega, we put down omega as a critical frequency whole square, omega c square, mu epsilon square root, where omega c is equal to 2 pi fc. Also we can put omega c m pi over a is equal to omega c square root of epsilon a. This is the obviously we have this relation, so we can put m the here the in omega c, so which is 2 pi fc, and omega c from here in this equation we can get fc is equal to m over 2a into 1 over epsilon mu square root. So since we have the omega from here, omega epsilon mu is equal to m square over 2a fc whole square. Now putting this value into equation 1, initial equation, gamma m is equal to m pi over square, which is 2 pi f whole square epsilon mu, further rearranging and cancelling the things which are in the denominator and numerator, then we are left with the final equation, which is m pi over a 1 minus f over fc whole square square root. Also, since m pi over a is omega c epsilon mu square root, so we can replace that value as well, omega c epsilon mu square root 1 minus f over fc whole square. This is equation number 4. Now for frequency below cutoff, where the f is less than fc, okay, this value f is less than fc, gamma m is real and fields are attenuated, and gamma m, that is equal to alpha m, as beta m is equal to 0. So attenuation is observed as the beta m is equal to 0. Only real part is the imaginary part will be equal to 0 for gamma m. The field amplitude decreases very rapidly in this condition. When gamma m is equal to alpha m, means decreases very rapidly with the distance z, because attenuation term e to minus gamma z, even though the phase will be constant. Now for frequencies above cutoff, when f is greater than fc, gamma m is imaginary, and obviously alpha m, the real part, is equal to 0. This whole thing is imaginary. So what we get, gamma m is equal to j beta m, gamma m is equal to j times m pi over a f over fc whole square minus 1, or again rearranging the things, we get j omega c epsilon mu square root into f over fc whole square minus 1. Question number 5. This condition is of interest because the wave propagation occurs without attenuation in the z direction. So attenuation, since alpha, here we don't have any real part, all part is imaginary. So while the real part consists the attenuation, so that means the wave propagation occurs without attenuation in the z direction. So that alpha part is 0, real part is 0, so that means the attenuation is 0 and the wave propagates without any attenuation along the z direction. In practical situation, owing to the finite conductivity of plates, some attenuation accompanies at a frequency above cutoff frequencies. A physical significance can be attributed to the critical frequency of cutoff by writing the expression. So fc is equal to m over 2a times 1 over epsilon mu. Since we can write the 1 over epsilon mu as a v, which is the velocity of the wave, phase velocity, fc is given by a equal to mv over 2a, but v, velocity of wave, is frequency times the wavelength, so it will be critical, so critical wavelength. So lambda c can be replaced by v over fc. that means from equation 6 we can get lambda c, the critical wavelength, is equal to 2a over m. Or a means, now a is the distance between the two plates, is given by m times lambda c by 2. This is equation number 7. Now the equation 7 gives the relation between the plate separation a and the critical wavelength lambda c. Thus the critical wavelength is fixed by the plate spacing. Okay, so as that at which the distance between the plates become exactly m half of the wavelength. So m of half of the wavelength, whatever, 1 half, 2 half, 3 half, and so on and so forth. M at m is equal to 1, we have lambda c by 2. M is equal to 2, we have lambda c exactly 1 wavelength, otherwise it will be, and so on and so forth. So that's is defining now the condition for the critical wavelengths, that is the separation between the two plates. For lower frequency or long wavelength are attenuated at higher frequencies, the higher frequencies or shorter wavelength are propagated without loss. The largest value of the cutoff wavelength is 2a, this is the maximum when m is equal to 1, that is lambda c is equal to m. Here we have the relation. If you go back, m lambda c, so lambda c is equal to 2a by m. So lambda c will be equal to 2a. M is the smallest mode, which is a 1. So lambda c is equal to 2a, which is the maximum separation between the two distance, the plates, separation distance. So the wavelength is the largest value of the cutoff wavelength is 2a when m is equal to 1. This means that the longest free space wavelength a signal may have and still be propagating in the plane, parallel plane guide, is just less than the plane separation. So the field components of the transelectric M waves with the propagation purely imaginary part are given as EY, C1, 3C. All those equations of the parallel plane waveguide, conducting plane waveguides, are just the alpha part is being placed as equal to 0, rest is the imaginary parts. So this will be the configuration figure of the wave propagation. This is for the E field, this is for the H field, and you can see here this is a lambda by 2. If the m is equal to 1, so wavelength is lambda by 2, the plate separation is lambda by 2. So this is along y-axis. Remember that z-axis is obviously perpendicular to the plane. So we have the E fields are along x. This is the x distance, which is the between the plates. This is the y dimension. So that's the field configuration for the EY will be aligned in this manner. While here we have the H, so it's a EY, the field pattern or field function. Here we have HX. Now HX field function, it is again the half of the wavelength, this more that one, and since it is the tangential part, it will be the H field component along x will be having these patterns, these two patterns will be followed. Okay, with this we reach to the end of the topic. Inshallah, see you next time. Thank you.